meantime, let me introduce our next speaker. Our next speaker is Mojtaba Abaie by Shoushtary. He joined the Institute for Research in Fundamental Sciences, which is ICM, as a research staff in 2016. He has been pursuing his PhD in computer architecture at article known as the political theory of University at Abaie in 2020 under the supervision of Professor Antonio Gonzalez. His research area is computer architecture and compiler optimization specifically for GPGPU. Let's get started.
Yeah, thank you so much. Can you see my screen? Can you hear me?
Yes, I can.
Let's get started.
Okay, let's get started. My name is Mojtaba Shoushtary. I'm presenting one of my recent works that is called Malekeh, and it is a lightweight register file caching scheme that is implemented in collector units for GPUs. First, I will give you some motivation and background on this topic. Then I continue explaining the microarchitecture. Then I will move on to the cache policies and issue scheduling that we developed to maximize the benefit of this scheme. In this scheme, we also implemented an adaptive algorithm to unleash the full potential of maximizing both bit ratio and the IPC. Then I will show you the methodology and the results, and we conclude the talk. So GPU register file has always been one of the main challenging memory components and chip. This graph shows the size of each on-chip storage in different generations of NVIDIA architecture. If you see that in all the generations, GPU register file has always been one of the biggest components in the chip, and the size has been growing. Not only that, for example, in Volta generation, 60% of on-chip storage is dedicated to the register file. It also consumes about 24% of dynamic energy and requires also a high bandwidth. For example, in this case, it requires 384 bytes per clock to provide enough registers for the peak performance of the execution units. If you in this slide, I will show you the contemporary register file architecture of GPUs to mitigate the challenges of designing the register file. Register file has been using many banks instead of a monolithic multi-ported design. In this design, we have some components that are called operand collector units, and the operand collector units just buffer the operands before dispatching the instruction to the execution units. In the operand collector units, we have a valid and a ready bit per each operand. The valid bit is to show that this entry is used, and the ready bit is to show that the value has been collected. It means that the value has been received from the banks. And beside each valid and ready bits, we have the data that is the is a vector register for each operand. This design has some issues. For example, it has high read and write energy consumption because the banks are huge, and there is also port conflicts on the banks. So the idea is to use a cache as a solution to mitigate these problems, but potentially the cache can also cause some problems and deteriorate the benefit of using the cache. For example, let's assume we have a cache that added in this stage. We fill the cache with the output of SIMD units, and let's assume the policy for the cache is write back. So in this scenario, we may create also new problems that we have to mitigate. And solving those problems may be complex and also reduce the benefit of using a cache. For example, we create write conflicts in the cache. If we assume that the ports for the cache should be limited, we also have conflicts in the evictions we cause because of the write back policy. In the cases we need to copy back the dirty values of the cache to main register banks, we create new conflicts. And also, we have some problems because this cache is implemented apart from the collector unit. So in the case, let's assume we do the tag check and we create a request to the banks when the instruction is sitting in the operand collector unit. So we may evict that value before the instruction reaches the SIMD units, because we did the tag check and we have a delay between the tag check and when the instruction receive all the operands and will be executed. We have also some reallocation penalty if we decide to share this cache between VARPs. So if a VARP replaces it, claims the cache, we have to flush all the values back to the main register file, and it may create some performance penalty. To solve these issues, we were thinking of designing a cache that is lightweight and reuses all the resources we already have on the chip. For example, in this proposal, we were aiming to create a lightweight cache in the collector units. In the collector units, we already have storage to keep the values. We have minimal pipeline modifications because this component is already integrated in the pipeline, and we have minimal extra operand routing networks. For the same reason, this component is not apart from the original pipeline. It's already there. And we were focusing to unleash the full potential by tailoring the policies. And we observed that the policies can have enormous effect for efficiency of this system. So the microarchitecture for Malekeh has changed this way. We keep the collector units, but we change the collector units to function as a cache and also the collector unit. It is doable by adding some controlling fields such as tag, alloc, bit, and reuse distance, and some least recently used field to keep track of LRU replacements. We also have some indirect indexes to the entries because we want to avoid the replicated values. We want to minimize the size of the cache table. So it's very, very important to have only one copy of each register. And we design a control logic to manage this system both as a cache and a collector unit. We also changed the way of scheduling and the allocation of collector units because this is the way that we know which warp occupies each collector unit, and to avoid the potential incoherence issues, we decided to limit each collector unit to one specific warp. So at any particular cycle, all the warps that occupy the collector units are different. This is this is handled by the issue scheduler and the CCU allocator. We observed that by this design, we need only 8 entries in the cache table, which is minimal modification because for our ISA, we needed already 7 entries in the collector unit. So this is only adding 1 extra entry to this design. So we are using the reuse distance. This reuse distance has been provided by the compiler, and the aim of this parameter is to increase the efficiency of the policies we define. First, I define the reuse distance. By reuse distance, I mean the number of dynamic instructions between 2 users of the same register. And as I said, it improves the efficiency of the policies. And it could vary during runtime due to the control flow behavior and the thread divergence handling mechanism of the system. To mitigate that effect, we approximated it with compiler by using some profiling information. And the approximation is pretty simple. We just approximate the reuse distance to 1 bit, and this bit shows the reuse distance is near or far. We compare the reuse distance with a threshold that I call RTHLD. If the reuse distance is less than the threshold, it means it is near. If it is bigger than the threshold, it means the reuse distance is far. And this threshold has been set empirically. We swapped a range of the values, executed different benchmarks from the beginning to the end, and we found the value of 12 that provides the best hit ratio on IPC for the whole experiments. Now, I will explain a little bit the cache policies we defined. First, I will explain the cache replacement policy. In the cache replacement policy, we use 3 fields in the cache table. First is the lock bit. The second is the reuse distance. And the third is the LRU field. The lock bit is to just lock the entries that are for the instruction that is waiting in the collector unit for the values to be received from the main register file. We need those values to be received when we want to dispatch the instruction, so we are not allowed to replace those entries. The lock bit will make sure that this entry will stay in the cache. So the policy has changed a little bit compared to a traditional LRU. First, as I mentioned, we ignore the lock bit, the lock entries to make sure the values will not be corrupted before dispatching. Then we randomly replace the far entries. And if there is no far entry, we will replace due to LRU. It improves LRU's effectiveness because replacing a least recently used entry can replace a near reuse, and it is suboptimal. By randomly replacing for entry, if any exists, we improve the effectiveness of this replacement policy. We also define the right policy based on these observations. We had the observation that in our benchmark sets, we have long reuse distances, and as we are using a one-level warp scheduler, there's a high chance of reallocation of the CCU by a new warp. So in this system, when we aim to reduce the size of the cache to make it efficient, and when we use the write-back policy, we have the issue of frequent write-backs to the main register files. We also have the issue of performance penalty because during the write-backs, we cannot use the collector unit. We have to lock it. And this is one of the precious resources of the chip. We have only 8 collector units and 32 or 64 warps. Like a collector unit can have performance penalty. Write-through policy also can waste energy because it puts the values in the cache that will never be used, and we replace them later. Write only in the register file also has some suboptimal behavior because in the write only in the register files, next time we have a reuse of a very near value, we need we will have a miss. So we need an extra read from the main register file. So the solution and the defined policy we have in this system is that we always keep the register file updated, and we filter the writes based on the reuse distance. We only put the values that have near reuse distance in the cache. And we also have another optimization is that to keep the overhead small, we only assume one write port per each collector unit. And for the warps that all aiming one collector units, we only pick one and discard the rest. Our analysis shows that this policy has minor effect on the compared to the cases when we assume infinite bandwidths, infinite write ports for the collector unit. The other approach we take is to allocate and fill, and the idea is to avoid the pollution because we have a small number of entries in the cache, and there's a chance that we never be able to write to the cache due to the fact that maybe the scheduler and the CCU allocator replaces the collector unit, and the writes when happens will never arrive to the cache, never arrive to the collector unit. And during the time, the value is going to be produced in the write back. The sources of independent instructions can also be put in the cache and benefit from the reuses that they have. So with this scheme, we have no performance penalty because we will not wait for any writes, and we can flush the cache instantly in any cases. Okay, in this slide, I will show you the issue scheduling policy we have. First, the issue scheduling policy will determine which warp occupies each collector unit, and it affects both the performance and heat ratio. Our observation was that using a two-level schedulers, that is very common in these designs, to reduce the number of active warps that share the collector units or the caches, has a performance penalty. In some cases, I observed that 40% performance penalty in some applications. And cache information also, we observed that has some hints, and those hints can improve the effectiveness of this policy. We also had the observation that some programs can tolerate delaying the reallocation of the CCU to new warps, and in those scenarios we delay the reallocation of the CCU, benefit from the potential reuses, and we don't damage the IPC. So based on these observations, we designed the issue scheduling and collector allocation policy. This policy is coordination of three policies. One is the issue scheduling, the other is the CCU allocation, and we have some waiting scheme that delays and postpones the reallocation of the CCU for a new warp. So first, we define the priority that the scheduler considers to select a warp. We prioritize the warps that having data in the CCUs or the rest of the warps. And always in each category, the oldest warps has higher priority. Then when the warps has been selected, we check that if that warp has data in any of the CCUs, we just allocate the same CCU to that warp, and we issue the instruction. If the warp is new, it means that there is no collector unit that has the data for this warp. We see that if there is any collector unit that all the values it contains are far, then we use that collector unit, allocate it, and issue the instruction. But if all the collector units have at least some near value, it means that all the collector units have the high chance of being reused very soon. Then we use a threshold and the counter to determine that we will replace that collector unit, or we can wait a little bit to increase the chance of the reuse of the values that those collector units contain. This threshold is called STHLD and has been set by one adaptive algorithm. The adaptive algorithm takes into account the characteristics of the applications and tries to set the optimal threshold based on the runtime behavior.
Yes, we actually run out of time, so could you just finish this presentation within like 1 or 2 minutes? Is it possible?
Yeah, I don't think so, no.
Yeah, how much time do you need?
Okay, 5 minutes.
5 minutes? Okay.
Yes.
Yeah, let's do that.
So the adaptive algorithm is per SAM, per chip, and the counter is per SAM. So based on the expected behavior of the STHLD, the heat ratio and the STHLD, we have such curve in our minds. We see that the heat ratio should be increased when STHLD is increased, and the IPC should first increase because we have higher heat ratio, and then it will decrease because we make many bubbles. We observe that in the real applications, we also have similar effects. Based on these effects, we created a dynamic algorithm. The dynamic algorithm works because we have homogeneous GPU cores, and these GPU cores are very regular. So the IPC will be stable for a long time, and we have some fluctuations. Because of that observation, we just partition the execution to multiple intervals, measure the IPC in the end of the current interval and the previous interval, and we compute the relative IPC change. Relative IPC change is small. It means that the IPC is stable. And if the IPC change is large, fluctuation is large, so it means that we are not in the same phase of the application. So the adaptive algorithm is described by this state machine and works based on this IPC fluctuation, tries to set the threshold for the next interval based on the fluctuation. And the idea is that, assuming the characteristic we expected, it can walk through a curve and converge to the optimal point that maximizes both IPC and heat ratio. This is how the execution of a sample works for this dynamic algorithm. It walks over the curve and reaches to the optimal point. For the methodology, we have the config for Turing car, and we use the cycle accurate performance model implemented in Axel Sim. And for the energy evaluation, we extended the model of Axel Watch for the register file to model the modifications we have. For the benchmarks, we have Rodinia and DeepBench. Our evaluation shows the 10% improvement in the IPC and about 50% heat ratio. And for the dynamic energy, we could save about 30% of the energy. Concluding this talk, we have a lightweight register file cache. We could repurpose already existing operand collector units. We added only some extra fills, minimal pipeline modifications, and we designed the policies to increase the efficiency of the system. For the results, we observed 10% speed up, 50% heat ratio improvement, and around 30% energy saving. Thank you for your patience.
Thank you so much. Any questions? So let me just quickly ask one question. So there were some register file caches published in like several years ago. So can you compare quickly with one or two studies that you remember, if you remember?
With which one? Register file cache papers, you mean? In this paper, we compared with one of those papers called Bow. And compared to Bow, we show that this scheme has better performance, better heat ratio, and also better energy saving. But if you mean that how this idea is different from Bow or those schemes, well, do you mean that I have to comment on this?
Yes, just quickly, just briefly explain what are the key differences between.
Okay. Compared to the Bow, we have the same approach that we implement the cache also in the collector units, but Bow is designed based on capturing locality within a sliding window of a few instructions, but we completely manage the system as a cache. And we share the collector units. In the Bow, the collector units are private to each warp. They don't talk much about the sharing effect, the scheduling effect, and how these things can affect the system.
Okay, got it. Thank you so much. There was one question in the chatting window. So this was asked in the earlier one of the earlier pages. So you can just answer through chatting window after looking over, right?
Okay, thank you so much.
Thank you. Okay, so we're gonna have